So we're going to go through some of the key concepts that will be covered on your quiz, either Wednesday or Thursday. And the first one, let's get our system of organization set up here. Your main idea and question column. If you're not going to take these notes, at least, take mental note of these main ideas. But the calculation review might be soaking up most of your time. I know things got a little bit squeezed at the end there, but hopefully you feel prepared when you walk in for this quiz. So the first main idea, remember I'm going to give you these. I'll tell you some questions, but you're going to have to write them. And I'm not going to give you your notes, but I'll tell you where to find them. First main idea is periodic motion. So we all know what motion is. Periodic just means that the motion is moving in a cyclic pattern. So there's two different major types of periodic motion or cyclic motion that I need you to know about. I'm not going to state what those are, but I will tell you where you can find the two types of periodic motion is in your do nows, or the do now answer from May 4th. You can find that in your pretest. This is going to be questions 2 and question 3. So hopefully you're not writing this down in your notes. What you're writing down is the answer to this question, or maybe you want to read this question and read this pretest and check out your simulation, the solar cycle simulation. I think on the title of the document though it says gravity and orbits. That's numbers 2 and 3. And then finally your circular motion reading notes. This is what you did on Friday in class. Check out number 2. Okay, so these are the things that you're going to want to check out to take these notes. But the main thing that I'm going to want you to be able to do is describe the two types of periodic motion. And what I'm going to need you to do is give me two, I guess you could say, time units. So there are some units of time that we use when it comes to periodic motion. We're talking about periodic motion of things in our solar system. So please be ready to describe those two types and tell me what units of time are defined by these two types of motion covered in these questions, these do now, this reading lesson, or this question from the reading notes. Okay, so moving on to your next main idea. A question you might want to ask for this one real quick is, what are the two types of periodic motion? Or once you get to these questions, you might come up with something a little bit better. Okay, so our next main idea that we're going to want to make sure you're familiar with when you walk in for the quiz are lunar cycles. So, short of just telling you exactly what this question is going to be about, there's many cycles caused by the motion of the moon. There's really one key one that I want you to know for this question, and we covered it in the do now on April 30th. It was on your pretest. Pretty much what I'm talking about here when I'm referring to lunar cycles is on number 22. Your solar cycle diagram I'd say the majority of this diagram was spent trying to model this lunar cycle. And finally, the video, not that I posted, but that it was probably Connor Bozeman, or maybe the new ones that I've been trying to post, give you something new to complain about. The video from April 29th. So check out these 4 things to see what I'm talking about here. But the main thing that I'm going to want you to state when it comes to this question is I guess I'm going to be looking for 2 main reasons for our observation of this lunar cycle. So there's really 2 things that you need to know. Why we see what we see, and why what we see is different at different times of this cycle of the moon, which is just the moon revolving around the Earth. I gave you a little answer there from the last question. All right, try to be a little bit more explicit about the main ideas from here on out, but those last 2 I was trying to be cryptic because I wanted you to look up and see what I was talking about. Get you in the habit of finding answers that you should already have rather than waiting for me to give them to you. So the next main idea is about the Earth's seasons. So the due now on April 27th covered the reason for the seasons. The pretest, numbers 18 and 19, kind of went into the technical vocab behind the 2 extremes, like the first day of summer and winter, and the first day of fall and spring. Memorizing those words isn't going to help you, but if you understand the transition that occurs on those days between the 2 extremes, that will help your understanding. The video that you were supposed to watch in class the day that we started this unit, it was either Wednesday, April 25th, or Thursday, April 26th. And then finally, your solar cycle diagram. So these are the 4 things that you're going to want to use to prepare you for the question on the season main idea. There's going to be 2 main things that I want you to know. You know, why we have the different seasons. That could be a question that you write here. But I want you to know kind of why it is when we're talking about the orientation of Earth relative to the sun. And I want you to know why it is when it comes to the sunlight hitting the Earth's surface. What's different about the sunlight hitting the Earth's surface at different points throughout the year during these different seasons. So check out the video. That's another thing. The video that goes along with this diagram instruction, I try to explain it in great detail. So if you're not quite sure why we have seasons, both on the large and small scale, then check out the video where I explained it to give you some help. Because if you didn't watch this video, maybe you weren't here this day and you don't understand the pretest answers, you're going to have a tough time with this question. Okay, so the next main idea, similar to the last 2, is all about eclipses. So there's 2 main types. It was covered in the due now on 5-2 if you are in 1st, 3rd, or 5th period, or 5-3 if you are in 2nd or 6th period. These 2 types of eclipses are mentioned but not really explained in great detail on the pretest. Numbers 14 and 15. And then this was mentioned in the gravity and satellites reading notes. And that was question number 14. So check out your 14th note, or since you got the document on Monday, you should just look at that question and hopefully the answer that you wrote down. And then finally, there was a video posted, or not finally, second to last thing, there's a video posted that you're supposed to watch for May 5th, and your solar cycle diagram. A lot of resources for this main idea, and this includes the video that goes with it, not just your finished product, but the video that shows you about the process. So study all of these. I'd say look at all of them, and then in these notes write down maybe what the two different types of eclipses are, and I would say the position, that's the key thing here that you're going to need to know. You're not only going to want to name these, but you're going to want to be able to describe, let me back that up, the relative positions. So where the Earth, Moon, and Sun are relative to each other. So the relative positions and the names of each. I think this is a 4-point question. You have to name them and describe them. So you could write that here, name and describe the two types of eclipses. Okay, pretty much the last conceptual main idea before I talk about the relationships are tides. So there's daily tides and monthly tides. But in order to understand the monthly tides, you have to understand the daily tides. So I'm going to test you on the monthly ones, but make sure you understand what causes the daily ones. So the due now from May 1st, covered tides. The pretest, question numbers 16 and 17. Name the two different types of monthly tides, the gravity and satellite reading notes. This was a series of questions, 10, 11, 12, and 13. So I'm just going to write questions 10 through questions 13. So 4 questions for this reading, or for those reading notes that goes along with this main idea. The video that you're supposed to watch on the evening of April 30th, and then finally your solar cycle diagram. And you have the video that went along with that, the instructional video of how to do that. So this is everything that you need to study right here. This is very similar to the last question. You're going to have to name the two different types of tides and describe the orientation of Earth, Moon, and Sun during each of those monthly tides. But make sure you understand what a tide is and what causes it, because you'll need that information before you can talk about what happens on a monthly basis. Alright, so the next thing, and the last thing pretty much, is going to be about the relationships. But I think that in order to discuss the relationships, we should first just write down the formulas. And that I don't have a problem giving to you now. Alright, this is a plural for formula. I say formulas all the time, but I think I'm supposed to be saying formulae. So let's write down the formulae you're supposed to have. The centripetal force equation is equal to the mass of the object that is moving in a circular or elliptical path multiplied by the centripetal acceleration. The rate at which it's changing direction depends on the force that's causing it to move in a curved path. You're going to have the formula for centripetal acceleration. That's equal to the square of the tangential velocity, but we're going to treat all of our objects as moving in circular orbits, so the tangential and orbital velocity will be the same. So the square of that velocity divided by the radius gives you centripetal acceleration. You know what, let's go ahead and write the units next to each of these, because that might be the difference between some of you passing and failing, or at least getting half of the points. So the units for force, that's newtons. Maybe let me put it on the other side over here. So we should all remember force is measured in newtons, which is a kilogram times a meter per second squared. Acceleration is measured in meters per second squared. So this is meters squared divided by second squared divided by meter, cancels out that square meter to give you meters per second squared. Okay, so the next one, velocity. Now usually this is orbital velocity, but right now we'll treat all of our velocities as one and the same. 2 pi times the radius, that's the circumference of a circle, divided by the period. So velocity is in meters per second. This is all these units. This is review. Nothing new when it comes to the units. Next equation is new, but very similar to something that's old. Newton's gravitational constant multiplied by the smaller mass times the larger mass. It could be mass 1 and mass 2, but I'm going to stick with this for now, divided by the square of the distance between them. Okay, so the other two main ones, and you know the units for force right here. So the other new one is the period of a planet's revolution. This is the most scary equation from this unit, maybe from this year. 4 pi squared times r cubed divided by Newton's gravitational constant multiplied by the mass of the object that is, the mass of the object that is causing the other mass to move. So that's an important distinction to make. Let me try to draw that a little bit better. Oh, here we go again. Let me try and fix this real quick. So this mass right here, this is the mass that is causing something to orbit around it, whereas this is the period of the thing that's doing the orbiting. So if I draw a little picture over here, this is the larger mass. This is the mass that is orbiting the larger mass. This period right here is talking about the time that it takes for the smaller mass to move around the larger mass. So that's why I'm using uppercase M in these two equations. It's just easy to associate something that is more massive with the letter that is capitalized. So this lowercase m and this lowercase m right here, this is this mass right here, the one that is doing the moving. And it's being attracted by the larger one that's causing it to move in a curved path. So keep that in mind. It might throw you off tomorrow or Thursday. All right, let me get rid of that picture so I can get our last formula up here. The last formula is the escape velocity. And this actually isn't an equation. I kind of made a mistake in the video yesterday. I should have said the escape velocity has to be larger than Newton's gravitational constant multiplied by the larger mass, so this is the uppercase one, the mass that's causing the smaller one to revolve. This escape velocity applies to the object that's revolving, but this larger mass right here applies to the mass that's causing the smaller one to revolve, divided by the distance. So yesterday I was using this as an equal sign, but think about the escape velocity. The velocity has to be larger than this value in order to escape its orbit. If it's equal to, it will stay at a perfect orbit, and if it's lesser than, it will actually eventually crash into the star. So treat this as an equal sign tomorrow. Forget about this inequality. Actually, let me just draw this whole thing over again, because for those of you that aren't actually listening to this, it might throw you off. Alright, so these are the 6 formulae that you'll have on the board. The other thing that you're going to need is Newton's gravitational constant. Okay, now we can start talking about what relationships that you're going to be held accountable for. And it's important to have these in front of you while we're talking about this, because if you understand these formulas, you should be able to easily understand the relationships. And before I do that, I just realized, let's write the units for these. Period is always in seconds. I would like you to remember it's seconds per cycle or seconds per revolution, because we're talking about a planet revolving around a star. But if you just write seconds, I'll take it. And then this is the same right here. I think the only other units you might have to worry about is for distance or for mass. But that's it. Everything should be straightforward. Alright, so I'm going to give you a series of relationships that you might be expected to know. And yeah, I should have made this page a lot longer, but there's nothing I can do about it now, so I might just have to rewrite things a bunch of times. So suppose that I asked you about how the period of a planet, so let's say T sub P, the period of a planet, is affected by the mass of a star. So I'm using uppercase M to represent the mass of the larger of the two, and stars are always going to be larger than planets. So what gets plotted along the Y is going to be the period of the planet. It's affected by the mass. The mass isn't affected by the period. And then we're going to put uppercase M down here. So the thing that is going to throw a lot of you off is what you are keeping constant. So let's look at our equations here. What contains period and mass? This one has period but no mass. This one has period. This one has mass. So we can see here that mass is in the denominator position. Period must be inversely proportional to mass. Now what in this equation has to stay constant for this variable, or for this relationship to not change? Well, 4 is constant, pi is constant, g is constant. There's only one thing in here that could change, and that's the radius. So what I would continue to write in my title is what would have to be constant in order for this inverse proportionality to exist. So you should know by now what this line looks like, and you should know by now what the expression looks like. It looks just like the equation. We're just getting rid of all of this stuff. Alright, so back all this up. Should have kept that there. let's say that I wanted you to know about the period of a planet versus its radial distance. So, actually, well, we're going to have to do it. Come on. So if I ask you how the period of a planet is affected by its radial distance, the distance affects the period and not the other way around. So the period of the planet goes here, the radial distance goes here. Same formula from before. Now you don't want to, you could look at this one, but you'd have to move period over here. So instead, let's look at this one again. What's going to happen to this value, or what happens to the period if the radius goes up? Well, since this is in the numerator of the fraction, if this goes up, this goes up. So you have a direct proportionality. Now what's going to have to stay constant? The only other variable in that formula is the mass. I'd like you to know that it's the mass of the star, but if you just write constant mass, you'll get that point. So you do need to add this in order to get all 4 of the points for those 2 problems on relationships. Okay, so let's keep this going to the next possible relationship that you'll have. And then this time, keep my title constant. Okay, so another thing that you might be asked is how the velocity of a planet is going to be affected by the radial distance. So how far away it is. So how far away it is isn't affected by how fast it's moving. How fast it's moving is affected by how far away it is. So the velocity of the planet depends on the radius. So let's look at our problems here. So you might be tempted to look at this one and say, okay, the radius goes up, that must mean that the velocity goes up. That's going to be the first thing that a lot of you tend to do. However, you have to be careful here. The radius of how far away it is affects the period. And if the period goes up, what's going to happen to the velocity? If this period goes up, it's going to go down. So since radius affects period, this is not going to remain constant, but this is going to go up, or this is going to cause the period to go up a lot faster. I guess the way that I need to describe this is the radius does cause this to go up, but since it causes the period to go up a lot faster, it's going to cause the velocity to go down overall. So this is what's called an indirect relationship that is leading to a direct relationship. So that's confusing. It's not inverse. But so the radius goes up, causes the period to go up. The period goes up, causes the velocity to go down. So it is inverse, but it's also indirect because of this 2-step process. So what has to remain constant here? Well, the period can't remain constant because it's affected by the radius, but the mass has to remain constant in order for the radius to affect the period and in turn make that period decrease the velocity. So you have to have a constant mass again here. So just to try and recap as quick as I possibly can. An increase in radius causes an increase in period, and an increase in period causes a decrease in velocity. Even though this causes this to go up, it doesn't cause it to go down as fast as period did because of this exponent right here. Okay, that's probably one of the tougher ones. But if you remember the simulation, we showed something like the closer something was, the faster it was moving. All right. next possible relationship that you could be accountable is going to be how the force of gravity is affected by the mass of the objects. So if I make gravity stronger, the mass of the objects doesn't change. But if I change the mass of the objects, those objects will be attracted to each other more. So the force of gravity depends on how massive the objects are. But that's only if look at this as a constant. We're talking about these increasing. If these increase, it's going to cause this to increase, but only if the distance between them is constant. So this is only going to be true if they are at a constant distance. So you just have to look at these equations and ask yourself, how do these variables depend on each other, and what else in that equation could change, which must not, in order for me to detect a relationship. So next thing that you might have to know is how the velocity of a planet is affected by the mass of the star. So if I have different planets moving around different stars and those stars have different masses, it's the velocity of the planet that gets affected by the mass of the star. How is that going to change it? Well, there's only two equations that have this connection, and it's an indirect connection because there's no mass and velocity. I guess over here, kind of true. Well, it is true, but this is escape velocity, which definitely is related to this. But anyways, I want to talk about this. So if the mass goes up here, that's going to cause the period to go down here because this is in the denominator. So anything that goes up here will make this go down here. And if this goes down here, then that's going to cause this to go up here. So the more massive a star is, the faster the planets will revolve around it. But that's if we keep them at a constant distance. So same kind of principle as last time. All right, almost done, getting close. I want you to know how the force of gravity may be affected by the distance between the two masses. So the force of gravity gets affected by the distance and not the other way around. I mean, if two things are attracted to each other more, their distance will change because they'll be pulled towards each other, but we're talking about how far away they are and how that affects how strongly they are pulled towards each other. So that's only going to be held true if this and this have a relationship and I forget about the constant. I have to keep my masses constant in order for that relationship to hold true. So this is going to be when the masses are held at a constant value. In order to see this, should be obvious. It's an exponential inverse proportionality. Okay, almost done. Last two, I want you to know how centripetal acceleration is affected by the centripetal force. So if I have a stronger force, what will that do to the rate at which my object is changing direction? So normally these two are flipped around, but this is actually not the way that the equation was originally written. When Newton gave the second law, and it wasn't with the centripetal force, but it doesn't matter, it was actually written like this. It was solved for acceleration. So acceleration depends on force. Force does not depend on acceleration. So this is the way that it should be taught, but this is the way that it's usually introduced. So the acceleration is obviously going to be directly proportional to the force, but that's if and only if the mass remains constant. So you know how to draw this graph, hopefully, and you know how to draw the expression at this point. You should. Okay, last one. I want you to know how the centripetal acceleration is affected by the radial distance. So how does changing this value affect this value? What happens to the rate of changing motion if I increase the distance between two objects? So the centripetal acceleration depends on the radius, and if this radius goes up, you should know that this value is going to go down. Now that's only if I keep a constant speed. Now that kind of doesn't make sense. Remember, acceleration, centripetal acceleration, has to do with a changing direction. I can't have a constant velocity, but I can have a constant speed, which is just the rate of its changing position. Not how quickly it is changing its direction, but how fast it's changing its position in any given direction. Now, if this one's throwing you off, you could, I guess, factor in mass here. The mass of the object will have an effect. So we could also say at a constant mass, because if that object's mass changes, it's going to have more inertia, and that will have an effect on the rate at which it changes its position, because it's going to have more of an inclination to remain in a straight line rather than be curved around by the centripetal force. You could also say that there's a constant centripetal force. Just anything that could have an effect on centripetal acceleration has to remain constant in order to detect a relationship between this variable and this variable. Okay, so that's it for this last video. Hopefully it will make your life easier when you take this test.